In this video, we're going to learn how to rationalize a denominator. The goal of rationalizing a denominator is to get a rational number out of the denominator of a fraction. So when we say to put something in simplest terms, it implies no radicals can go on the denominator of a fraction. So there are two flavors of rationalizing the denominator. The first one might look like something like this. The square root of 7 divided by the square root of 3. And the second type of problem that you might see might look like 8 divided by the square root of x minus 1. So what makes these two different, the two different flavors, is that in this first one, there is just one radical on the denominator. And then in the second one, you have a radical and then adding and subtracting some other number. Could be another radical, or maybe it's just a plain number. But the way we rationalize these denominators is different. So you want to look for one term or multiple terms. And then that will tell you which direction to go. So let's try a couple examples, and we'll do some of each style. So the first problem, we'll take the square root of 7, divide by the square root of 3. So we want to rationalize this denominator. To do that, this hinges on this fact. If you take the nth root of x to the n, the answer is going to be x. And we want to make sure that x is going to be a positive number, so 0 or larger. No negatives in this case. So our goal is to create an x to the nth power so that when we take the nth root and nth power cancel each other out, and you're just left with the x in the middle. So I need to create this denominator so that I get 3 squared. So because there's a hidden 2 in our index on both of these, but only focus on the denominator one, we need to somehow figure out how to get a 3 squared so that the square root and squared cancel each other out. So what we do is we always multiply our fraction here by something so that we get a perfect square on this denominator. So in this case, I need to have 2 3's, so I need to multiply by an extra square root of 3, because now I will have 3 times 3, which is 3 squared. But we can't just multiply the denominator by anything we like. We need to also do that to the numerator. So the numerator gets multiplied by the square root of 3. And what we've basically done is this fraction, because the same thing is on the numerator and denominator, is equal to 1. So we're multiplying by 1, and we're not changing the value of our answer, we're just changing how it looks. Okay, so let's keep going. We're multiplying 2 radicals. So I'll go across the top and multiply, and then go across the bottom and multiply, because they're both radical numbers. They both have square roots, so you can multiply the numbers underneath the square roots. So we're going to have the square root of 21, 7 times 3. And then on the denominator, we are going to have the square root of 9, because 3 times 3. And now we get to simplify. The square root of 21 doesn't simplify any further. There's no perfect squares that go into 21, but 9 is a perfect square. Square root of 9 is 3. And we are done. This is the equivalent version of the square root of 7 divided by the square root of 3, but there is no longer a radical in the denominator. So we have simplified the problem. We are done. And if we really wanted to, we could go to a calculator and check these two answers just to make sure that they come up with the same value if we really don't believe we did it right. All right, let's try another one. But this time let's use a cube root power. The cube root of 3 to the 4th. I'm going to start off by splitting up this radical. So I have the cube root of 3 divided by the cube root of 4. And I really want to emphasize that I need to have an exponent of 3. So the cube root of 3, that's just going to repeat. The cube root of 4, so 4 is 2 squared. So 2 is 1 less than 3. So I need to multiply the denominator by an extra 2 so that I can rationalize this denominator. So my extra fraction over here, which will be equivalent to 1. So equivalent to 1. I have 2 2's, but I need 3 2's. Again, that's to use this fact, nth root of x to the nth. So I need to get 2 to the 3rd power. So I'll have a cube root of 2, because now I'll have 1, 2, 3 2's in a row, and then do the same thing on the numerator. So what we come up with is the cube root of 3 times 2, and then on the denominator we have the cube root of 2 squared times 2. Now I wrote it out like this just to really emphasize how many 2's are repeating. I could go to my next line and say, okay, well this is the cube root of 6. Done, that's the numerator. And then on the denominator I have the cube root of 2 cubed. So the cube root and the cube cancel each other out. We're left with the cube root of 6 divided by 2. And we know we're done because there are no more radicals on the denominator of our fraction. For our third example, we'll bring back the cube root, but now we're going to use some variables. Let's take 7 divided by the cube root of x. So if we have a variable or a number, we use the exact same process. We need to get x raised to the 3rd power so that the cube root and the cube cancel each other out. So I will multiply by whatever I need so that I have 3 x's. Well, if I have 1 already, I need 2 more. So the cube root of x squared. There's my 2 more. And then do the same thing on the numerator. Again, this is our magic 1, so we're not changing the value, just the way this looks. So the numerator becomes 7 times the cube root of x squared. Nothing to simplify there. This was a plain old number. Here's our radical, and we'll just keep them just multiplied like that. We can't really simplify and clean it up a little bit. Now in the denominator, this is all cube root. So if I have 1x and I multiply by 2 more x's, that's 3 x's. So now I can simplify even more. 7 times the cube root of x squared all over x. And we have just rationalized the denominator. So again, the whole point is to get the exponent of the number under the sign to match the index of the radical. And then they cancel each other out and you get a plain number. No more radicals on the denominator. All right, let's do one more with a higher order of index. So let's do 6 divided by the 5th root of 8x cubed. So in this problem, we have numbers as well as variables in this denominator. So that means that I need to get something raised to the 5th power and then x raised to the 5th power so that this radical goes away. So let's do a little bit of math over here off to the side. So 8 is 4 times 2. 4 is 2 times 2. So we know that 8 is 2 cubed. So I'm going to rewrite this. 6 divided by the 5th root of 2 cubed times x cubed. And now I can easily compare the exponents that I do have compared to what I need to have. And that will help me figure out what I need to multiply by. So both the numerator and denominator will have a 5th root. That always has to stay the same. So if I have 3 2's, but I need 5, I'm short by 2. So 2 squared. Because now when I multiply these radicals together, I have 3 of them over here, 2 of them over there for a total of 5. If I have 3 x's over here, I need to have 2 more, so I get my x to the 5th. And then on the numerator, just repeat everything. 2 squared times x squared. All right, so let's combine all this together. 6 times the 5th root of, I'm going to say 4x squared. I'm going to go ahead and multiply those out. I know this isn't going to simplify anymore, so I might as well just write the 4. And then on this denominator, I have the 5th root of x, oops, let's put in the number first, 2 to the 5th times x to the 5th. Now we see our 5th powers and our 5th root, so we're going to get to cancel out to get just the base. So our last step, 6 times the 5th root of 4x squared all over 2x. Now there's one more step we need to do on this problem, and it is to reduce my fraction. I looked and saw that 6 and 2 have a common multiple, or have a common factor, 2. 2 goes into 6 and 2 goes into 2. So I'm going to simplify a little bit and say 2 goes into 2 once, 2 goes into 6 3 times, and then rewrite my answer 3 times the 5th root of 4x squared all over x. So sometimes that might happen, especially when you have longer problems that have a lot more variables and a lot more numbers. Give a good look at the last step of the problem and see if there's any more reducing that could happen. In this case, it happened to be numbers where I could do some reducing, so I did, and now I have a completely simplified problem.